There is a 5-minute window, that is all you get. From the moment a perfectly fried batch of French fries comes out of the oil, golden, crackling, impossibly light, you have approximately 5 minutes before the crunch begins to die. Not degrade slowly, not fade gently. Die. The texture that took precise oil temperature, the right potato variety, the correct fry time, and years of operational knowledge to produce, gone in the time it takes a customer to find their table, unwrap their food, and take their first bite. If you work in QSR, you already know this. You have watched it happen 1,000 times. You have received the complaint: soggy fries, soft fries, fries that taste like they were cooked an hour ago even though they came out of the fryer 8 minutes before delivery. And most operators respond to this complaint the same way. They fry fresher batches more frequently. They turn up the holding temperature. They tell the team to move faster. None of those things fix the actual problem. Today we are going inside the fry, the chemistry, the physics, the moisture science, and the 5 engineering solutions that the world's most successful QSR operations use to keep crunch alive long enough for it to matter. Welcome to Season 2 of Plate Store Places. I am Rahul, chef, food engineer, and someone who has spent a genuinely unreasonable amount of time thinking about potato starch. 3 books for this episode. 1. The Food Lab by J. Kenji Lopez Alt. I have mentioned this before, and I will keep mentioning it because his chapter on French fries is the single most rigorous and readable breakdown of fry science I have encountered outside of a food technology journal. He double fried, he triple fried, he tested every variable. If you want to understand what you are actually doing when you put a potato in hot oil, this is the place to start. 2. Coatings Technology Handbook. This one is for the food engineers and QSR operators in the audience. If you are working with battered or coated products at any scale, this handbook covers moisture barrier science, starch behavior, and coating system design in the kind of technical depth that will change how you look at every product you produce. Not a casual read, an essential reference. 3. Food Physics by Ludger Figueira and Arthur Teixeira. This book covers the physical properties of food, texture, structure, mechanical behavior, with enough clarity that a chef can follow it, and enough rigor that a food scientist will find it useful. The chapters on crispness and fracture mechanics are directly applicable to everything we are discussing today. Right? Let us talk about what is actually happening inside your fry. Most people think crunch is simple. You cook something until it is dry and rigid and it crunches. Remove the heat and it softens. End of story. It is not end of story, not even close. Here is what is actually happening. A raw potato is roughly 80% water and about 17% starch. When you put that potato into oil at 175 to 185 degrees Celsius, 2 things happen simultaneously. First, the water inside the potato begins to boil and escape through the surface. You can see this as the vigorous bubbling around the fry when it first enters the oil. Second, the starch granules at the surface of the fry gelatinize, swell, and then dehydrate as the moisture escapes, forming the rigid, porous, glassy crust that produces the crunch you are chasing. That crust is the crunch. It is a thin shell of dehydrated, gelatinized starch with a network of tiny air pockets inside it. It is rigid because it is dry. It is flavorful because the Maillard reaction, the same browning chemistry that makes seared meat and toasted bread taste complex, has been running across its surface during the fry. Now here is the problem. That crust is extraordinarily hygroscopic, which means it absorbs moisture from its surrounding environment with almost no resistance. And the surrounding environment, the moment your fry comes out of the oil, is absolutely full of moisture. The steam coming from the hot interior of the fry itself, the ambient humidity of the kitchen, the moisture released by other fries sitting in the same container. And if they are in a closed bag or box, all of that moisture has nowhere to go. It condenses, it is reabsorbed by the crust, And the moment starch reabsorbs water, it loses its rigidity. The air pockets collapse. The glassy structure softens. The crunch is gone. This is called starch retrogradation and moisture migration, and it happens fast. Measurably, the crunch of a standard fried potato product begins to degrade within 3 to 4 minutes of leaving the oil. By 8 minutes in a closed container, it is significantly compromised. By 15 minutes in most standard QSR packaging, you are eating something that is texturally closer to a boiled potato than a fried one. The temperature of the fry accelerates this process. A hotter fry produces more steam faster, which means more moisture reabsorption faster. Holding your fries at a higher temperature under a heat lamp does not slow moisture migration. It speeds it up. The fry is doing the damage to itself. And here is the detail that most operators never consider. The enemy of your fry's crunch is not the air around it. It is the fry next to it. A single fry in an open container will hold its crunch longer than a pile of fries in a closed box, because each fry in that pile is releasing steam into a shared enclosed space, and every fry is absorbing moisture from every other fry simultaneously. The more fries in the box, the faster the collective moisture environment degrades the crunch of the whole batch. This is why the fries at the bottom of the box always go soft first. They are bearing the weight of the pile, and they are receiving the most condensation from above. Let me tell you about a QSR chain I worked with that was having a very specific and very frustrating problem with their fry ratings. Their fry product was genuinely good. The potato variety was right, the oil was well maintained, the fry time and temperature were dialed in precisely. In kitchen taste tests, the fries were excellent, crispy, well seasoned, flavorful. Their operations team was proud of them. But their delivery reviews told a completely different story. Fries arriving soft, fries arriving limp. One reviewer wrote, and I remember this specifically, "These fries have given up on life. We did what I always recommend when the kitchen and the customer are experiencing different products. We ordered from the platform ourselves. We timed everything. We opened the box at the 22-minute mark. The fries were soft, not dramatically, not offensively, but soft. The crunch that had been there 10 minutes earlier was gone. We went back and measured the moisture content inside their standard delivery box at the 20-minute mark. The internal humidity inside the sealed container was high enough to have fully compromised the starch crust on every fry in the batch. The fix was not the recipe, the fix was the box. They switched to a vented container with a ridged base that elevated the fries above any condensation pooling at the bottom. Crunch retention at 20 minutes improved significantly. Delivery ratings for fries recovered within 3 weeks. Same recipe, same fryer, different box. Here is another story from a food manufacturing project I was part of earlier in my career. We were developing a coated fry product, a fry with an engineered batter designed specifically for extended crunch retention. The brief was simple: create a fry that holds acceptable crunch for at least 30 minutes in a delivery environment. Straightforward enough in theory, genuinely complex in practice. The first formulations we tested used a standard wheat flour and cornstarch base. Good initial crunch, gone within 12 minutes in a closed container. We pushed the starch ratio higher, better. Gone within 16 minutes, still not enough. The breakthrough came when we introduced modified starch, specifically a cross-linked starch that had been chemically altered to resist the absorption of water even after gelatinization. The cross-linked starch formed a more robust moisture barrier in the crust. It did not prevent moisture absorption entirely, nothing does, but it slowed the rate significantly. The final formulation, with the right ratio of modified starch, rice flour, and a small amount of methyl cellulose as a hydrocolloid binder, achieved consistent crunch retention of 28 to 32 minutes in a vented container within spec, deliverable at QSR scale. That project taught me that the crunch problem in fries is not one problem. It is 3 simultaneous problems: the composition of the crust, the packaging environment the fry travels in, and the holding conditions between the fryer and the customer. Solving one without the other two gives you partial improvement. Solving all three gives you a product that actually survives delivery. One more story, and this one is short, but the lesson is large. I know a chef who runs a small but genuinely excellent QSR operation. His fries are cooked from scratch. Good potato, clean oil, precise timing. He had never had a crunch problem with his dine-in customers. When he launched delivery, the complaints started immediately. He responded the way most operators respond. He started frying to order for every delivery ticket, thinking freshness was the answer. His fry times got longer, his kitchen got slower, his ticket times increased, his other food quality suffered because the fryer was occupied. And his fries still arrived soft because frying to order does not solve the packaging problem. It just moves the clock slightly. When I sat with him, the conversation lasted about 20 minutes. He was solving the wrong problem. The fries were fresh. The crust was forming correctly, but the packaging was sealing in every molecule of steam the fries produced and returning it directly to the crust. We changed the packaging to a paper sleeve with natural ventilation, added a ridged liner at the base, and adjusted his delivery radius to ensure no order was traveling more than 18 minutes. 3 changes. No recipe change. No operational overhaul. Crunch ratings in his delivery reviews went from consistently poor to consistently strong within a month. The fry was never the problem. The fry was being destroyed by the environment it was traveling in. So what actually works? Here is what the evidence and experience consistently shows. Solution 1. Engineer your coating for moisture resistance, not just initial crunch. A straight flour dredge will give you excellent crunch in the kitchen and almost nothing in a delivery environment. Add rice flour to your coating mix. It gelatinizes at a higher temperature than wheat starch and forms a harder, less hygroscopic crust. Add cornstarch for additional rigidity. If you are working at scale, investigate modified starches specifically designed for extended moisture resistance. The coating is your first line of defense against moisture migration. Treat it like the engineering decision it is. Solution 2. Double fry your product. This is standard practice in high-quality operations but still surprisingly rare in QSR. The first fry at a lower temperature, around 150 to 160 degrees Celsius, cooks the interior of the potato fully without heavily browning the surface. The fry is then rested and cooled, which allows the surface starch to set. The second fry at a higher temperature, 180 to 190 degrees, creates the final crust rapidly and with much lower residual moisture in the interior. A double fried product starts with significantly less internal steam to reabsorb. It holds its crunch longer from the very first minute out of the oil. Solution 3. Vent your packaging and elevate your product. This is the single change that delivers the most immediate improvement for the least cost. Your fry container needs to breathe. The steam your fries are producing must be able to escape rather than recirculate. A vented lid or a paper sleeve with natural breathability will extend your crunch window measurably. Add a ridged or textured base inside the container to elevate the fries above condensation. A fry sitting in pooled moisture at the bottom of a box is being actively destroyed by the packaging. Lift it off the surface. Solution 4. Control your holding temperature and time with discipline. Every degree above your optimal holding temperature accelerates moisture migration from the fry interior to the crust. Every minute beyond your defined maximum hold time compounds the damage. Define your hold time limit. For most uncoated fries, this should be no longer than 4 to 5 minutes. For coated fry products, depending on your formulation, you may have more runway. Write this into your operational protocol. Train your team to discard and refry at the hold time limit, not when someone notices the fries look soft. By the time they look soft, the crunch is already gone. Solution 5. Manage your delivery radius as a quality variable, not just a logistics variable. Your fry has a crunch lifespan. Your delivery radius determines whether the fry reaches the customer inside that lifespan or outside it. Most QSR operators set their delivery radius based on what is operationally convenient or what the platform allows. The correct approach is to set your radius based on what your product can survive. If your fry holds acceptable crunch for 18 minutes and your rider takes 25 minutes to reach the outer edge of your radius, you are systematically delivering a failed product to a portion of your customers. Tighten the radius or engineer the product to extend the window. One of those two things has to give. Solution 6. Consider par cooking and finishing on order for high-volume delivery operations. This is a more operationally complex solution but delivers excellent results. Par cook your fries to 80% doneness during prep. Hold them in a dry, cool environment. When the delivery order comes in, finish the fry in hot oil for 90 seconds to 2 minutes. This gives you a freshly fried crust on a fully cooked interior with dramatically reduced internal moisture because the long par cook has already driven most of the interior water out. The finishing fry produces maximum initial crunch with minimum internal steam to reabsorb. The crunch window is longer and the product consistency is higher. Quick facts before we wrap up. Fact 1. The global market for extended crunch fry products, commercially coated fries engineered specifically for delivery hold time, has grown significantly in the last 5 years as delivery platforms have expanded. Major potato processors now offer delivery-specific fry lines as a standard product category. If you are buying commodity fries for a delivery operation and wondering why the crunch does not survive, the answer may simply be that you are using the wrong product for the channel. Fact 2. Nitrogen flushing, the same technology used inside crisp and chip packets to prevent moisture absorption during shelf life, has been explored for hot food packaging in delivery contexts. Several packaging innovators are currently testing modified atmosphere containers for QSR applications. The principle is identical. Replace the humid air inside the container with an inert gas that does not carry moisture. It is not yet mainstream, it is coming. Fact 3. The ideal oil temperature for the final fry from a crunch retention perspective is 182 to 185 degrees Celsius. Below that, the crust forms more slowly and retains more moisture. Above it, the exterior browns faster than the interior can drive out its steam, producing a crust that looks perfect but has trapped moisture behind it. That trapped moisture then migrates outward and destroys the crust from the inside. The temperature window for optimal crunch is narrow. Fryer calibration is not optional. It is quality control. Your challenge this week. I am calling it the #crunch clock challenge. Order fries from 3 different QSR or delivery operations this week. When each order arrives, start a timer before you open the packaging. Open at the 1-minute mark and rate the crunch on a scale of 1 to 10. Then open a second portion of the same order at the 8-minute mark and rate it again. Document the crunch decay. How fast did each one fall? Post your results on Instagram or LinkedIn with the #crunchclock and tag me. Tell me the operation, the packaging type if you can identify it, the delivery time, and the crunch scores at 1 minute and 8 minutes. This is real data. I want to see it. The most methodical test and the most revealing crunch decay curve gets a shout out next episode. That is it for today. The 5-minute crunch window is not a limitation you have to accept. It is a design problem with engineering solutions. Coat for moisture resistance, double fry for a drier interior, vent the packaging, control the hold time, tighten the delivery radius, consider par cook, and finish systems for high volume operations. Your fry does not lose its crunch because frying is imperfect. It loses its crunch because the environment it travels through after frying has never been treated as a design variable. Treat it as one. The crunch will follow. Next time on Plates to Places, we tackle topic 5, why fried chicken turns rubbery under heat lamps, and whether the holding drawer is secretly running a sauna for your best-selling products without anyone's permission. Until then, respect the crust, control the environment, and give your fries a fighting chance. I am Rahul, and this is Plate Stow Places.